really this concept of integrated distribution system planning is near and dear to kind of what my career has been about. So within that context, right, we're going to talk about forecasting loads and DER and kind of how that's done, but with a real emphasis on the context for kind of how these things are used, right? What distribution system planners are thinking about when they're looking at different forecasts. Jessica, could you hit the next slide for me here? Thanks. Yeah, so we're going to set the stage, right? What are distribution system planners thinking about? Why does forecasting matter? I'm going to run through a couple of examples and then kind of talk about forecasting in the context of scenarios and various things. Throughout the presentation, you'll see I like pictures, so I've got a number of graphics that are on here. And then also I think things are fairly well sourced. They may be a little tough to read, but I think everybody's going to get a copy of the slides so that you can kind of follow along or follow up on various things. So next slide, please. Yes, so IDP forecasting. So we're talking about load and DER forecasting in the context of distribution planning. And that's important because I would spend my 15 minutes very differently if I were thinking about it in the context of bulk system planning, resources, transmission. But since we're talking about kind of distribution planning, I have to start with getting our minds into that space, right? And so when we're doing distribution planning, we have to take kind of three kind of broad buckets of data and include those in our distribution system planning forecasts. First broad bucket, right, is our system-wide high-level projections. So on the left, this is ISO New England's system host is spotlighting your video. Okay, so on the left is our ISO New England kind of bulk system peak load. And when we're doing distribution planning, we need to also include our kind of granular data around what's going on a given feeder, on a given circuit, at a given substation, right? So that data could include sensors we've got at the substation, maybe somewhere along the line, we've got some line sensors, or maybe it's built from our advanced meters that can tell us exactly what's going on at each customer location. But then, we need to also include kind of local knowledge, right? What's going on in the neighborhood, what's going on in the community that might not be readily apparent in our historical data, or is kind of noise in the bulk system kind of long-term plan, right? So this is, I just pulled one example from kind of an older news outlet around neighborhood revitalization plans, right? So distribution planners need to have kind of their ear to the ground on developments, different kind of trends that are going on, and how those might represent a stepwise change in the historical data that's been seen. So we have three broad buckets. Jessica, if you could hit the next one for me. And those forecasts, right? We come up with the forecast. I'll get into a little bit more of how that's done, but I want to make sure that we really emphasize what we're using that forecast for. So this all comes from Excel's 2021 IDP and how they think about their annual distribution planning process. So they've got this kind of circular thing going on where, let's start with the load forecast, right? Or we've got our existing system infrastructure, right? So we've got our current state, and then we layer on some load forecast. We understand, okay, what does that load forecast mean in terms of risk to different system equipments? Hey, let's come up with some solutions, some mitigation plans for that risk. Think through how that might improve, what the most cost-effective way to mitigate that risk is. Hey, and then let's build it, or let's start that project, right? Let's execute on different plans. And then, hey, once we've got a new kind of current state, a new reality, then the whole process starts again, right? What's next? What's coming up next? And a lot of utilities, most utilities do this annually or roughly annually. And what they're looking for usually, right? Most of what I'm characterizing here is a usually. There's 3,000 utilities out there. I don't know exactly how all of them do everything.
Sean, you're frozen.
I am frozen.
Now you're back.
I've been fighting my internet all day. Hopefully that does not persist. I'm going to stop my video here, see if that helps a little bit. So we're talking about capacity utilization. A lot of here, Excel shows their desired utilization percentage is 75% for their distribution equipment. That's roughly aligns with what I would expect. They don't want to use everything at 100% all the time because they want to maintain some system flexibility for moving loads around on the distribution system, maybe to allow for some time for a new project to be built, right? So this kind of threshold allows the distribution planners to examine that specific case a little bit more closely, right? Something may be past the threshold and they choose not to initialize a new project right away, but it's on their kind of watch list or something like that. So what we're really looking for is different distribution system equipment that could potentially be overloaded. And then kind of characterize what that overload might be, right? So here we've got an overload for let's say our substation transformer is rated to be able to carry 10 megawatts. Man, at 6 o'clock, it looks like it's going to be overloaded by a megawatt. And then it comes down to some engineering to kind of better understand if that's a real problem, if there's maybe some solutions that could be used to move things around, or maybe we just need a bigger transformer there. So we're taking our load forecast and we're going to better kind of engineer our system based on what that load forecast is telling us. So next slide, please. Yeah, so how do we get that load forecast? Here's one example. Generally, we're trying to take our kind of high-level system-level model and make it spatially granular, right? So that we can analyze what's going on in a given substation, on a given circuit, and better kind of translate the broad policy goals, energy efficiency targets, different things to a specific feeder level model, right? A specific circuit. So there's some tools that can help with this, help calibrate the two models, help merge different data sets that maybe don't totally agree. But ultimately, what I liked on the way that National Grid presented this is it shows the multiple kind of data points, and maybe it's not even data, maybe it's just kind of goals or trends that go into the forecast, right, and the range of outcomes. So ultimately all these different kind of pokes and prods and variables are used as an input into the distribution planning tool, right, into that engineering tool. And there's a few different ways that this is done. On the next slide, we get into how Hawaiian Electric thinks about that, right? So I like this representation in terms of showing how a new development layers on top of existing trends, right? So this is across different months, across different years, what does our load shape look like, right? And so, here's our existing infrastructure, how that varies by hour of day. And then, I've got a new neighborhood going in. So I know roughly how a new neighborhood can, when folks are going to use electricity when that new neighborhood goes in. And then, that varies by month, by time of day, maybe it varies by year, right? We're expecting different trends that come across in 2028 that may not be present in 2019. And so by layering these things on top of existing, we're able to see how close we get to that, our distribution system ratings. But it's important to say, understand how these different pieces fit together, right? So our new neighborhood doesn't necessarily use electricity, exactly when we want it to, overnight in this instance. Maybe it's added, maybe the peak for our new development is added directly to the existing peak. Maybe it fits neatly, in the overnight hours or somewhere else. So this is a granular kind of translation of our kind of locational knowledge, our broader kind of trends that we see in the industry or in the data. Jessica, could you get the next slide for me? So one of the things that's done here is, okay, new development that's helpful, but we can go a step further than that, right? We can say, hey, we know how at my house, I know when the air conditioning is running, I know when I use the dishwasher, I know time of day for lighting, right? I have my home office, so I know when my charge needs are being fulfilled. And so we can, on a kind of broad basis, we can understand how the overall load across a broad network can be disaggregated into individual components, right? So we can say, hey, what's our, okay, we know our kind of load shape throughout the day. How much of that is made up of air conditioning or indoor lighting or clothes dryers? And from there, we can better take apart and understand what we need to target, right? How that might impact our distribution planning activities. So this slide includes a couple of graphs that I did 7-8 years ago for the good folks in Minnesota. It also includes some data from NREL, National Renewable Energy Lab, that was just published, I think officially last year, maybe this year. But the idea is that we can, by disaggregating, by looking at the individual end uses, we can better understand how our electricity consumption is made up. And that allows us to look at our baseline performance, right? We know historically, this is when folks used air conditioning, but hey, maybe we invest in more energy efficient air conditioning that might shift around when that load shows up. Same thing for like televisions or residential refrigerators, right? All sorts of different things can layer on top of each other to create different daily profiles or seasonal profiles. There's a lot of really important implications of disaggregating the load data. One of them is that it allows you to isolate the impact of temperature, right, of climate on load, right? So when it's hot, folks are using more air conditioning. Simple enough, but quantifying the exact impact can be a little bit more challenging. Similarly, the impact of electrification on load profiles, right? So in the Northeast or across most of the country, where all of a sudden we're going to electrify heating demand, what does that look like, right? When does that show up? Is it mostly overnight, right? Is that when we want it to show up, or are we going to need certain trends to have different kind of heating shapes that maybe are more beneficial for the system planning? So in the context of all of this, I haven't really talked a lot about how the forecast is made, and part of that's on purpose, right? We could talk a lot about math. I love some machine learning. All those things are very fun, But at the end of the day, there's so many variables at play here that I think it's really important to understand kind of how these things stack on top of each other to create ultimately the forecast that gets used in our engineering tools. So if we go to the next slide, I'm going to get a little bit more into what the distribution system planners are looking at. Okay, so when we're doing distribution planning, we've got our model of the distribution circuit. And along that model, we've got our kind of AC power flow that shows us our voltage at different points along the feeder, right? So we can say, hey, we're a mile from the substation. Our voltage is a little bit lower than right at the substation. We've got some losses along the lines. We've got various things going on that cause our voltage to drop a little bit. Similarly, right, that's made a little bit more complicated by the presence of DER, particularly unmanaged solar. The graph on the right here shows how at the distribution transformer, you see relatively steady voltage, but any given customer, or in this instance, a specific customer, can experience dramatically different voltage levels outside of the kind of safety guidelines due to the presence of unmanaged solar production. So the kind of the lesson that I'm trying to convey here is how all these things kind of stack on top of each other. We've got a whole lot of different forecasts, a whole lot of different variables, and we're trying to get it to a kind of hyper granular level, right? So it's not just, I know where 5 million electric vehicles are showing up in California, or whatever the number is. It's really hard to come up with that number. It's even kind of more of an errand to translate it to a given substation. And then, hey, even if we get it right at the substation level, in order to do the distribution engineering around it, we've got to understand where on the circuit, those electric vehicles or those generators, those distributed generators, right, or rooftop solar, where exactly those show up, right? Because that has the impact of affecting our distribution planning, our infrastructure investments, or our kind of programmatic approaches to different things. So, do you go to the next slide? So this leads us into, there's a lot of uncertainty, right? In terms of, we're trying to take these various policy goals, this high level of, statistical granularity, high level of data that's available through different sensors that are placed around the distribution grid. So we're trying to take all that, make sense of it, understand what our forecasts are, how that affects our future kind of grid needs. And so one key, one way to do that, one way to kind of, I'm going to say relax the problem space, is to adopt a probabilistic approach. So on this slide, we've got two probabilistic approaches that are shown. One is good work out of SMUD a few years ago with our friends at the Smart Electric Power Association, and I think Black and Veatch was their consultant. That I really like this graphic that helps us think through where different things are on the grid and how the various kind of end uses or various DER can impact our load profile, right? So we know solar has a certain profile no matter where it is, but how do those things kind of stack together? How do those things work together to inform our distribution planning? Below, we've got work from Portland General on their transportation electrification planning. So they're looking at where do vehicles dwell, right? What's their primary parking spot? And then how does that translate into energy requirements at a given place. And so by knowing, these couple of different pieces of information, we can start to drive towards, quantification measures for what type of DER will appear, where will they appear, what's our timing on that in terms of year, and then what's our timing on that in terms of, across the year, right? When maybe it exacerbates grid problems, or maybe it actually helps some of the forecasted grid needs. So one of the things I want to mention here is this probabilistic analysis technique is kind of new. A lot of folks are working on it. It's new both for our industry, but also there's some really novel things going on across industries to improve our kind of Bayesian statistical rigor outside of academia. So one of the key things that I think is taking off is on our next slide, around scenarios. We've got all these. What I've tried to convey is we've got all these different, different things, different variables that constitute our forecasts. And not only are they variables with respect to time of day, they're also variable with respect to individual locations. And so as our individual locations get more and more precise, the uncertainty of if our forecast is accurate, the uncertainty grows, right? So we're less confident in our forecast on any one location, even if system-wide we're pretty confident. So scenarios have kind of caught on as a way to help us think through things, help us understand the implications of different potential futures. So in 2021, Detroit DTE worked through a couple of scenarios that helped them assess the potential changes to the grid, what that meant, what are the implications over the next 15 years or so. This kind of approach was inspired by the Department of Energy's DSPX grid modernization framework, which kind of makes the case for forecast scenarios to identify kind of infrastructure requirements and enable analysis of locational DER. So DTE's approach I thought was a little novel in that their scenarios weren't just a high electrification, mid electrification, low electrification type thing. It was intended to more stretch a little broader than that, right? What does it look like in a high, what does our distribution system look like in a high electrification scenario? What does it look like if we have more and more storms that affect our grid? What does it look like if we've got a lot of solar PV that gets placed everywhere, or a lot of storage that gets placed behind the meter? And so the implications of those things, the particulars of what the forecast is a little bit less important, right? What is the electrification scenario? Is it 2%? Is it 3%? What does electrification mean is a little bit less important than what are the implications? What does that tell us? Well, as they put a number on it, distribution overloads began to occur at 2% adoption, right? So if they get 2% of vehicles on the road, or I think that's what they had there, all of a sudden, a lot of our distribution system starts to get more and more overloaded. And so the use of scenarios here helps us to get out of the kind of nitpicking around the particulars of a given forecast and get into more of the implications, more of utilizing what the forecast is telling us, right? Has it stretched our boundaries enough, right? Has the scenario looked far enough in the future, thought about how things maybe overlap, how things work together? Or has it maintained too much of a status quo, right? And so by using scenarios, we're able to kind of think through those things logically, as opposed to get kind of stuck in an argument over 2% or 3% of electric vehicle adoption. So if you go to the next slide. It's my last one. I think I was decent on time. All right, so what did we talk about? We talked about forecasts. They include three things: high level kind of trends, policy implications, a lot of granular data, right, that maybe is available through our advanced metering infrastructure, or substation data, or kind of anything else that's out there. But then also locational information that maybe we know because we're in the community. And then we talked a bit about probabilistic forecasting, how that can help us make sense of all this data, all this uncertainty, and really in particular around scenario planning and how that can help stretch the thinking beyond just the value of a given variable, without getting tied to a particular forecast. These scenario planning and distribution planning in general is about trying to identify changes that are needed, right, on the system. A lot of integrated distribution planning uses a 5-ish year horizon, and within that time frame, and particularly with the forecasting isn't the right word, particularly with the supply chain challenges that we've got, that 5-year horizon, a lot of the projects that are initialized today will change our reality over time, but the long-term forecast is a little bit less important to how those things get resolved because of the regular updates of these distribution system plans, because things are reassessed annually. That allows us to correct some of the forecast errors that maybe were inherent in our methodologies.